Section 4.8 Antiderivatives. A physicist who knows the velocity of a particle might wish to know its position at a given time. An engineer who can measure the variable rate at which water is leaking from a tank wants to know the amount leaked over a certain time period. A biologist who knows the rate at which a bacterial population is increasing might want to deduce what the size of the population will be at some future time. In each case, the problem is to find a function capital F whose derivative is a known function lowercase f. If such a function capital F exists, it is called an antiderivative of the lowercase function f. So the definition: a function capital F is called an antiderivative of lowercase f on an interval I if capital F prime of x is equal to lowercase f of x for all x that's in the interval I. Now in section 2.8, we introduced the idea of an antiderivative, and we learned how to sketch the graph of an antiderivative of f if we were given the graph of f. Now that we know the differentiation formulas, we are in a position to find explicit expressions for antiderivatives. So for instance, if we let the function f of x is equal to x squared, it isn't difficult to discover an antiderivative of f if we keep the power rule in mind. In fact, if capital F of x is equal to 1/3 x cubed, then capital F prime of x is equal to x squared, which is the same thing as lowercase f of x. But the function capital G of x is equal to 1/3 x cubed plus 100 also satisfies capital G prime of x, which is equal to x squared. So therefore, both capital F and capital G are antiderivatives of lowercase f. Indeed, any function of the form h of x, which is equal to 1/3 x cubed plus c, where c is a constant, is an antiderivative of lowercase f. The following theorem says that the function f has no other antiderivative. So for theorem 1, if capital F is an antiderivative of lowercase f on an interval I, then the most general antiderivative of lowercase f on the interval I is capital F of x plus c, where c is an arbitrary constant. Now going back to the function of lowercase f of x, which is equal to x squared, we see that the general antiderivative of lowercase f is x cubed over 3 plus c. By assigning specific values to the constant c, we obtain a family of functions whose graphs are vertical translates of one another. You can see the graph below here. This makes sense because each curve must have the same slope at any given value of x. So if we look at the first graph, it's going to be x cubed divided by 3 plus 3. It's shifted up 3 units. This one is shifting up 2 units, shifting up 1 unit. There is x cubed over 3, shifting down 1 unit, and shifting down 2 units. So again, these are the members of the family of the antiderivatives of f of x, which is equal to x squared.